Alright, let's talk about transformations, more specifically how we can take functions and their graphs and shift them left to right, up and down, or reflect them over the y and x-axis, or x-axis, and also to stretch them or compress them. So let's first look at the parent functions. So these are like the original graphs before we transform them. Alright, and this first one is f of x equals a constant. Now, that's just a horizontal line. Alright, f of x equals like a specific number. Like in this picture, it would be f of x equals 1. Alright, that's just going to be a horizontal line through 1. And the way I remember that is Hoy Bucks. Alright, horizontal lines are y equals equations, and f of x is like y. So if you see f of x equals like a specific number, you're just going to graph a horizontal line, and that number is going to be the y-intercept. Alright, and that's all you really need to know about constant functions. Alright, then you have linear functions. Alright, f of x equals f of x equals x would be the parent function, meaning it's the most basic form of that. So that would just be a line with y-intercept 0, slope of 1. Alright, now when graphing a line, I wouldn't really think of it using transformations. I would just use your rules like slope and y-intercept, or find a point on the line and use the slope to graph it. Alright, so transformations aren't really super important with lines. Alright, but absolute values, they could totally help you graph absolute value functions. Now remember, anytime you get stuck graphing anything, you can always just plug in random values for x, evaluate, see what y is, and then plot those points. Alright, now the absolute value of x is going to look like a v. Alright, that's because, alright, when x is greater than or equal to 0, it's going to be the line x. And when x is less than 0, alright, it's still going to be x, because if x was negative, negative x, because if x, which I'll highlight in orange, is negative, then these absolute values are going to turn it positive. So another way to do it would be to put a negative in front as a slope. Alright, and now you have, and now that's where the other part of this v comes from. Alright, so it's going to start off as a v with the vertex at the origin, and then you're going to shift it, translate it, or reflect it. Now, one fun fact about absolute value functions is that this number here in front of the absolute value symbols is going to be the slope of this line. So if you had something like y equals the absolute 2 times the absolute value of x, alright, that would just be a more narrow v, where this part of the line has a slope of 2, and this part of the line has a slope of negative 2. Alright, the square root function, f of x equals the square root of x. The parent function is going to start at the origin. And it's going to look like kind of like a half a parabola going sideways. Alright, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. Alright, so as x increases, y increases, but since y is the square root of x, y is going to be less than x in our parent function. Alright, then we're going to take this and shift it up, down, left, or right. Now, one thing to notice is that the domain for these square root functions is x has to be greater than or equal to 0. Now, that could change if it was shifted left or right, but keep in mind that when you take the square root of a negative, it's not a real number. So when you're graphing these, you're going to start and either go forever in one direction or the other direction if it's reflected. Alright, but you could think of a square root when you sketch it as kind of like a sideways half of a parabola. Alright, and here's an actual parabola. So when you have something where the variable is being squared, your graph's going to be shaped like this. Alright, if it's a parent function and it's not transformed at all, alright, the vertex is going to be at the origin, and then 1 squared is 1, 2 squared is 4. So as x increases, y increases, but y increases kind of more rapidly than x. So that's why it becomes more narrow as x gets larger. And then we're going to take this and learn how to shift it around. But if it's a quadratic function, your graph is going to be in the shape of a parabola. Right, and here we have a cubic function, which because when you cube a number, if it's positive, it's going to stay positive. If it's negative, it's going to stay negative. So instead of it kind of bouncing off the vertex like a quadratic does, this is going to always constantly increase or decrease, because, alright, yeah, 2 cubed is 8, but negative 2 cubed is negative 8. Alright, whereas if you were to square negative 2, you would get positive 4, which is why a quadratic looks like that. Alright, cubics, on the other hand, kind of look like a parabola, but if you took this part and like kind of folded it down, then you would have this shape here. So it's a constantly increasing polynomial, and you treat it just like a quadratic when you're analyzing the type of transformations, but the picture is going to look more like this, kind of like a snake, like an increasing double-sided parabola. Alright, and here's the greatest integer function. What this does is it takes whatever's inside these parentheses looking stuff, and so it's like brackets, and usually it's sometimes it's written like this, and it's going to round down to the greatest integer less than x. So if you have something like 1.5, it's going to round down to 1. So that's why these kind of look like steps. It's also known as like a step function. So if you know that this is the basic parent function, then you could transform it. Alright, in the next video I'll show you what the transformations do, but those graphs I just showed you are where we're going to start when we're graphing.